But anyways, so derivatives, integrals, and vector functions. So first, we're going to define definition of a vector. So a definition of a vector is just like an arbitrary one, right? So let R be an arbitrary vector. So therefore, dr dt respect to t is our regular limit definition itself. Okay. Now, the good news is because we're already in, we've skipped that stuff, it comes to limits, roughly. We don't have to use limits because I know everybody loves limits, right? So we'll just go our basic straight out definition. So if our vector RT is respective f, g, and h, so what that means is each component is a respective function of t. All you have to do is take each one individually and then take its derivative. So you just take the derivative of each component individually with respect to t, and then we call it a day. That's our derivative vector. Now, one very key thing going forward as well is something called a unit tangent vector. Okay, so the unit tangent vector is just like its unit vector, but it's the derivative. So it's the tangent of it. So the unit tangent vector represented as t of t, so capital T of t, is the derivative of r divided by the length of r, or the magnitude of r. Okay. So that's going to be a key thing going forward as well. So that's going to be the tangent or the unit vector based off our derivative. So if we want to find the plane based off that, well, guess what we need, right? So what exactly is going on here? So if you want to, okay, got the derivative. So, but what does it mean to us in, in space? Which is a good question. So let's go back to our simple portions, right? Now, let's suppose I have this curvature in space. Now, again, this curvature can represent as different vectors. So let's suppose I have this point P here, and this vector that connects the origin to point P, we'll call that the actual vector R of t. So that's our regular, vector going from there to there. Now remember, according to the definition of anything, right, going back to way back to algebra, this T of H is represented as like X plus H, meaning so if I just keep going and just add H to it, I'm out here now. Let's say this is P and this is Q. So therefore, this vector connecting there to there, this goes back to, I think, the first question people had before, is what? R of H, T plus H minus R of T. Well, what happens if I, if eventually put these two together? Well, that's basically our definition of a derivative, right? The limit. The limit as these 2 points get arbitrarily closer together gives us the definition of a limit or the derivative itself. That's pretty much what we're doing with respect to vectors. Is eventually, as these vectors get arbitrarily close together, we get the derivative function itself. So that's pretty much what's happening here. That's what, the concept of the derivative of a vector happening in vector space. So that's like the theory behind it. But like everybody else, right, once you get into higher math, you get to, you like this stuff, but, as you guys are like learning it, it's like, okay, yada, yada, yada. How do we actually get, how do we use this, right? That's the main thing. But so a lot of these examples is pretty straightforward. So find the derivative of the vector. So RT, or the derivative of RT is just literally just the derivative of each component with respect to t itself. Okay, so we take the derivative each, or basically 3 times, respectively. Okay, so the derivative of this one, so 1 goes to 0, so it's going to be 3t squared I. Okay, and then we have the derivative of this. Now, anybody remember how to do that? It's a good old product rule, right? Yay, right? Remember, I have to refresh your memory on product rule. So remember F and G, product rule is F G plus F prime G. So do a little shortcut. So we'll call this T equals F, and we'll say g is e to the negative t. So the derivative of f is going to just be 1. This is going to be negative e to the negative t. All right, this is basically a chain rule, right? Derivative of the inside times the derivative of the outside. Derivative of the inside just -1 times the derivative just itself. Ready? Am I going too fast for everybody? Everybody got that? Okay, so I'm assuming all good. Okay. All right. So therefore, putting this all together, right? So it's going to be according to our rule, f times g prime. So just going to be t times that. Oh, 2 times. Yeah, that's right. So I'll just put this in parentheses to make it easier. So negative t e to the negative t plus that times that. J. So that was nice, right? So that's lovely. Plus, and notice again, good old chain rule, right? So just in case you guys forgot, so it's the derivative of the inside is a 2 times the derivative of the outside. Derivative of sine, I believe, is cosine, or positive cosine this time. Oh, this is a t. So plus 2 cosine of 2t k. And there we go. There's our derivative. So we want to refresh a little bit on derivatives. Don't worry, we're not going to go too crazy because we will actually be doing the chain rule later on with double derivatives and stuff like, or integration as well. But you may want to refresh your memory on some trig. That's pretty popular when it comes to our class itself. Just cosine, sine usually is enough, and then just a little bit of product rule wouldn't hurt either. Okay, so now that we have that, that's part A. Find the derivative. Perfect. Part B. Find the unit vector. The unit tangent vector at the point t equals 0. Okay. All right. So before we do anything, let's find the derivative at t equals 0. Make it easier for ourselves, right? So the derivative of t equals 0, that just means plugs in 0 everything we have, right? So 3 times 0 is just going to be 0. That goes away, and e to the 0 is just 1. And cosine of 0 is 1, so we just get 2. Okay. Now, the reason why I do this first, because remember, when it comes to everything in math, as you guys see in the quiz, you always want to think smart, not work harder, right? So remember, according to our definition of our unit tangent vector, it's the derivative at the point, which is what we have, divided by the length of the vector at the point. So if you already have the length at the point, therefore the magnitude is just going to be the square root of 0 squared plus 1 squared plus 2 squared. Right? There's no need to put that in here and square it, and then plug in zero for at the end. Just do it at the beginning. Make it easier for ourselves. So this gives us, square root of 5. So therefore, our tangent vector at 0 is going to be this vector divided by the square root of 5, or just 1 over square root of 5j plus 2 over square root of 5k. Questions there at all? All good so far? No, let's try another one. Okay, so find the Paramec equations. Find the Paramec equations for the tangent line with Paramec equations this. Okay. At the point 0, 1, and pi over 2. All right, so I'm going to tweak this a little bit just to help ourselves make it a little easier for ourselves. I'm going to get rid of this cubed here and just put t, since we're just, reviewing ourselves with derivatives. You could just do a t squared, you can see the difference there. Okay. So again, find the parametric equations for the tangent line, right? So first we got to find the tangent line, or find the equation for the tangent line itself. So remember, whenever you see tangent, what do? Take the derivative, right? No matter what, just change our rate of slope. So our vector is all of this, right, with respect to t, and it doesn't matter, right? It's all respect to t. So the vector is just 2 cosine t, 4 sine t, and then t itself. So therefore, our derivative is just going to be minus 2 sine of t. I'll do this time. 4 cosine, and then just 1. Two different ways to get comfortable with both ways of vectors. Okay, so now we're just going to plug in the point 0, 1, and then pi over 2. Now this is a trick question. Now we're plugging in the point 0, 1, and pi over 2. Now, notice I'm technically not going to plug in 0 and 1 because this vector is only with respect to t. And this is x, y, and technically t there. Okay. So just a little trick question. This value at the end is the t value you're going to plug in respectively. Because in most cases, unless you have like, x, yt representation here, it's always going to be in terms of t. Okay. So now, again, going back to unit circle, right? So if sine of pi over 2 is 1, so therefore this derivative is just going to be -2. Cosine of pi over 2 is 0, so 4 times 0 is 0. And u is constant, so just that, right? So there's our vector at the point. Now, given our point, our initial point, 0, 1, and now pi over 2, now we could find its parametric equations. Remember, it's a line, so we can find it. Okay. So now, x is going to be equal to, well, remember, it goes back to our equation, so it's going to be the point plus this times t, so 0 plus 2 times t, 1 plus 0 t, and then pi over 2 plus 1 times t. Or just clean it up. Because it's that. So this is the parametric equations for the tangent line at the given point. You guys may want to star this question. Yep. Questions, Arnold? Okay. So, because the derivatives follow the exact same template as we had previously, just like every old calculus portions, same thing applies when it comes to vectors. Okay, so all of these properties hold as well. So if you add in derivatives which given two vectors, you can take the derivative of each one individually. If you have two different function and unit vector, that's called the product rule, essentially. We can have the chain rule, quotient rule, and also obviously the well, we're not going to do integration by parts, but technically you can do that as well. That's another really hard concept to deal with as well. Okay, but that's for integration, but yeah. Okay. Oh, actually, the use substitution is also a pretty difficult one. We'll talk about that later on. Okay. But again, all these properties apply itself. Okay. Now, what we're going to be proving is number 4. Okay, so the dot product. So when you multiply two different vectors, right? So you get the two dot products, you actually get that itself. So in other words, the product rule. Okay. So let's suppose u of t is equal to u1, u2, and u3. And also v of t with its respective v1, v2, and v3. Yep. So therefore, u dot b, going back to our old definition, right? Just regular old dot plot definition, is the multiplication of each component added together. Like that. Now let's take the derivative with respect to t. Well, what does that mean, right? For each individual component, each individual component, it has respect of t, right? So this is, u1 of t, u2 of t, u3 of t, right? Just like f, h, and g we had earlier. Well, each one of these is a respective product rule. So according to our product rule, we'll just have u1 prime times v1 plus v1 prime times u1. And we do that all the way down. There we go. So now all I'm going to do now is collect all the u1s, u2s, and u3 primes and put them here, and all the v1s, v2, v3 primes and put them on that side. So in other words, I'm going to put that, and that together, this, and then that together. So I'm going to have u1 prime v1 plus u2 prime v2 plus u3 prime v3, and then plus the other one. So v1 prime u1 plus v2 prime v2 plus v3 prime v3. I just organize it in that format. Okay. So now, if I just look at that part there, and if I look up, that's our dot product. Right? That's v1, v2, v3. So that's v prime dot product with what? U prime. Plus, let's go over here. That's the u. So that's u prime, or u itself, dot product with what? V prime. So therefore, the derivative of u of t times v of t, or the vectors themselves, is equal to u prime of t dot product v of t plus u of t, these are all vectors, times v prime of t. There we go. So, and now the rest of them follow the exact same template. It's just pretty much algebra and manipulation itself. So far so good. Okay. Now, let's do an interesting question. Okay. Now, what do you mean by an interesting question? Is what if you have now arbitrary letters, right? Numbers are fun, but letters is what's the important part, right? The more theoretical part itself. Okay. So let's go to our first type of proof example. We want to show that the length of r of t of this vector is equal to some constant c. Okay. So if that's true, then the derivative of r, of the vector r, is orthogonal to r of t for all t. Now, if you guys remember, what does orthogonal mean? Perpendicular, right? Well, there's one way to show that two things are perpendicular. Their dot product equals 0. So that is what we want to show. So if I would multiply their respective dot products, I actually get 0. And that's what we want to do, given this being true. So we're going to start with that. So we're given this to be true. So the length of the derivative of r is equal to some constant c. Okay. Well, what if I just square both sides? Like that. Okay. Now, the next step goes way back to the first sections, is a quick little note. There's a very special dot product property that stated this. That. So therefore, if I translate this over here, this becomes oh, wait a minute, this is not prime. What am I talking about? That's not prime. No one said anything. Okay, here we go. R of t times r of t equals c squared. Okay. So now let's take the derivative of both sides with respect to t. Well, on this side, again, it's going to be product rule. And the derivative constant is just going to be 0. Well, these are the same thing. We'll divide by 2, gives us exactly what we wanted. The product there, the dot product is 0. So therefore, r prime is orthogonal to rt. So just a fun little example there to see how it's going to go along throughout the semester as well, and the different type of questions you're going to be seeing in this class. All right, so since we talked about derivatives, let's talk about integration. So to integrate a vector is the exact same process we would do for a derivative. All we're going to do is do the integral of each component of the vector individually. Now, because integration has a different concept, right? So remember, if you integrate, for example, if you take the integral of x, for instance, dx, this is going to be x squared over 2. And then we always use that plus c at the end, right? Remember that plus c, the constant, we don't know. So same thing applies with the integration of a vector. So we're going to add plus c at the very end to signify there is a constant vector being added to it at the very end. Okay, unless given to us into or in definite integrals, but in indefinite integrals, we'll always have that constant at the very end. Okay. So let's do some examples just on integration. You guys, a little review of integration. So given that r is equal to 2e to the t and secant squared x and 2t, okay, find the integral from 0 to pi over 2. All right. So we're just going to do integral of each one individually. I'm just going to do it all at once to make it easier. Of 2e to the t I plus secant squared t j plus 2tk. And I'm doing this for a reason, because sometimes if this is like a t and this is a t, I don't do what, I don't add 2t together, right? So you want to do each one individually. I know what the definition is, so if you want, you just do this if you like. But you could just do the little shortcut I was doing, just to remember that each one is an individual component. You're never going to be putting stuff together itself. All right, so at this point, we just take the integral. So the good thing is e to the t is itself, so it's just going to be 2e to the t. Derivative, or sorry, the integral of secant squared is going to be tangent. And the integral of 2t is going to just be t squared, right? This is t squared over 2, t's cancel, and just t squared. Okay. And then since we have bounds, we just plug in 0 to pi over 2. Okay, so this is going to be a while, right? So this is going to be 2 to pi over 2 pi plus tangent of pi over 2. That's going to be sine over cosine. Oh, it doesn't exist, right? So this is gone. And this is just going to be pi squared over 2 over 4. Minus 0. Tangent of 0 is 0. And 0. And this is I, so minus 2 pi. This is j. Sorry, forget about that. No, this is k. Sorry. So we have 0j and then pi squared over 4k. Sorry about that. Forget about it. We're still in vectors. And then at the end, we just add them together. So I'm just going to put this all in one big lumps. Like that. Try another one. So given r of t to be 2e to the t, same one, plus, okay, t minus cosine tj, and then 1 over tk. All right, so the integral, so no bounds this time, so just indefinite integral of 2e to the t plus integral of t minus cosine t plus the integral of 1 over t. So this is going to be the same at top, so this is 2e to the t plus this is going to be t squared over 2. Integral of cosine is sine. And anybody remember the integral of 1 over t? It's a very special property. Natural log. ln of t. Yeah. So this is going to be I. This whole thing is j. This is k. And because we have indefinite integral plus c. And there's our derivative. No questions? Okay, all good. So quick recap. We take derivatives just like old-fashioned way with each component individually. Therefore, we could find the tangent line to it using its unit tangent vector and the point on the line. And we can also take integration the exact same way as normally we did before. Why did we find the derivative with the integral? You mean in the same section or together? What do you mean by that? Are you talking about this example here or this page examples? This one? We didn't find the derivative. We found the, oh, whoops. Oh, I see what you're saying. My mistake. I want to find the integral. Let's do both. Sorry, got too excited with integration. I actually like integration, that's why. Derivatives get boring. All right, so let's find the derivative. This should be pretty straightforward. So derivative of this is just going to be 2e to the t. I'll go this way, it's faster. 1 minus derivative cosine would be plus sine t. And then derivative of that would be e to the negative 1, so negative 2. See that. Thank you for that catch. I didn't even read it. You got too crazy with integration. Sorry. Good catch. So technically the answer would be here. But if you don't, I could ask you for both.